Okay, I think that everybody who wanted to join us is already here, and I think we can start. So I will just quickly present myself. So my name is Daria, and I'm data scientist at Publicis Sapient. I joined very recently uh, this team, and but indeed I have quite some years of experience in data science and software development, and now I am just energetically drifting a little bit towards the direction of our data engineering. Uh, well, the topic for the presentation today. Um, I made it a little bit short, I think, but I think you're gonna get it with the explanations later on. So it's explain your model predictions with Lime. First, you definitely will ask which kind of model and then what is the Lime, but this is exactly what I'm gonna to explain you or try to explain you. And for the start, uh, okay, okay, I think it goes now. Um, for to start with the brief overview, just put a quick summary about everything I plan to cover. So first, I want you to get really engaged with the subject because I love this idea. I hope you're gonna love it as well. And I'm gonna start with explaining you why do we care about the explanations, why I do like this topic, and why you may like it as well. So I'm gonna go quickly through the basic definitions and concepts. So I think for those who are like new to this topic, they're gonna get it a little bit better where it all begins. Uh, Definitely because Lime is in the title of the presentation. Gonna tell you what is Lime, how does it work, try to explain with the simple examples what is all this thing about. And yes, I plan to give you a couple of and show you a couple of examples of practical application of Lime. And actually, what I want to illustrate, to demonstrate is that how Lime can add certainly some value to the daily work of data scientists. And I think we're ready to go. Okay, what versus why? As a data scientist, through my career, I often kind of face the situation when the first question we need to answer is a question what? Uh, so, what is the probability of an earthquake? What the optimal price for our product? What is the class of a tumor? What is the diagnosis of the patient? Uh, and so on and so forth. So typically we succeed to create a model which learns something from the data and can successfully answer this question what. But then when people begin using it, they begin to come up with the questions why, because sometimes the model does not predict well, or it makes mistakes, or indeed it predicts right answers, but it also make people surprised, and they recently come to you like with a question why it is the decision which model are provided. So how it all these things work? Um, they get this question mainly because for the users, uh, your machine learning model is typically a black box. So they shooting data in, they think that it makes some black magic inside, and it comes up with a prediction. And the prediction, for example, like you have a patient who came in, you give a questionnaire, the machine learning model kind of processed it, and it says, okay, the patient is most probably the guy is sick. So you need to pay attention to him. what would be really nice for the doctor who need to take a decision as a human is to really try to understand the rationale behind how machine learning model came up with this classification, right? Because it's like a binary classification. He's sick or not sick. And the model can highlight important features which really contributed towards the decision of the model, which says, yes, this guy, he's sick, he needs your attention, he has a substantial loss of appetite, he has fever, he doesn't suffer, however, from the headache. And so that can give you a hint which diagnosis to make or which specific tests you can just sort of do for the future and trying to understand better what to do. Okay. I think it's worth explaining early in this presentation what does the LIME stands for, because it's sounds weird. In fact, I decided to explain it a little bit here and attach it to a couple of basic definitions. So, in fact, LIME stands for, it's an acronym. It stands for Local Interpretable Model Agnostic Explanations. So I highlighted two things in this title, which is interpretable and explanations. So I found two definitions, like formal definitions, what is explanation. And as you probably saw and understood from the previous slide, so we can describe explanation as a collection of the features of the interpretable domain, which, for instance, doctor, like a domain expert, can understand. And these features actually contributed to a given example, to this instance, to this particular patient for which we process the data. These features made the main contribution towards the decision of the model. Okay, so it can be classification or regression or whatever. And the second thing, which is interpretable, and interpretation here is defined as the mapping of an abstract concept, for example, some predicted class, into a domain that the human can make sense of. And I'm not absolutely happy with these definitions. I think I need to make it more clear by using kind of examples of explanations and interpretations. So because you can get an explanation, it can tell you everything about what you need to know, but you may have a really hard time to interpret it as a human being. So imagine you make a text classification and you ask for explanation and you return the vector of numbers representing the indexes of the words in the text, which, for example, the model says, okay, these words at the indexes XYZ contributed to my decision that the text talks about the weather. To make it interpretable, would be nice if you just can read the text and the words are highlighted and you can understand yourself. Really, that's true. That's a text about the weather. The thing's getting even worse when you deal with the deep learning models, because they can return you word embeddings, and the words embeddings is even worse than the indexes of the words. It's like for human beings, it may have completely no sense, and it would be really hard for you to kind of deal with this information. So same for the images. You make a classification. You want to know if it's a cat or a dog, and your explainer returns your 3D array of pixels of the image, and it says, wow, here are your explanation. This is what I think about it. Indeed, I think masked or highlighted image zones will show you, like, for instance, the ears of the cat was the key decision driver for the model to decide that this is a cat, it's not a dog. Or you can make it even fine-grained, right? Like you have two images of the bugs, one a black bug, red bug with the black spots. So here you can clearly see that colors impacted the decision of the model to say, okay, this red thing with the black spots, it's a ladybug. So color impacted the decision. And it's more fine-grained than just the area, because yes, it detected there's a bug, but which kind of bug? That's the color. Our key message to take at this moment, that we need explanations. Explanations are important. but they also need to be interpretable for to add real value and to bring real value to end users. So to conclude a little bit at this moment, why do we care about explanations? So I think we agree that interpretable explanations can help us. So it can help us to let user understand rationale behind the model. It can help also user to access validity because he can check how model arrived to this decision and he say, oh yeah, yes, really, this makes sense. Okay, I agree. So it can help to support, or like it can get additional help for supporting your decision, because like it can highlight some important things to which you need to pay attention as an expert. Like a doctor should pay attention to the significant loss of appetite from the patient. It can tell you something. And indeed, we know that with the time, models can degrade, something can happen to the data. If you have a tool to control, like you have a way to control things at the exit, right? So just get more clear about why you get these results from your model. You can just understand, okay, things turned wrong. It's turned wrong because the model doesn't produce any more clear, good results, doesn't perform well, or maybe, wow, there's something changed with the data at the input. So it kind of helps us to raise the red flag. Things don't go well. So I take a pause for a moment, and I just want to ask you if this everything clear up to this point. Do you have any questions so far? Or you don't have questions and we can continue. Appreciate if you can mark in the chart something. Just say, okay, we are happy with your explanation, or we love more detail, or we got a question straight ahead to be answered because we cannot continue without that. Okay, sounds like everybody's happy. We can move forward. Okay, so what gives me really a little bit of problem is the delay. So I hope you see now the next slide, and it's meant here to tell you that explainability really connected to the model complexity. And at this time, we arrived to the dilemma. We know that machine learning model, they passed through the really significant evolution. So people kind of developed a lot of sophisticated tools in this domain, and tools and techniques. They let achieve super high performance, which sometimes your deep neural networks can really kind of exceed, and the prediction accuracies of human beings. But nothing comes for free. So the higher the model complexity, the harder it is to get it to get interpretable explanations from it. So the chart here, I don't know if you can see my cursor moving. So the chart at the right was actually produced in the process of a DARPA study, and DARPA is this sort of a defense advanced project agency in the United States. I'm not sure about the abbreviation. But they really studied, like, that, for instance, your decision trees, they're nice, cute, simple. You can easily explain them because this is a sort of kind of easy to illustrate, easy to visualize, easy to make it interpretable. But they are not so much performant. When the last architectures are of the neural networks, they are super performant, but they are really hard to explain. So then we kind of facing a question: can we get maximum performance while keeping the possibility to explain pretty much any model prediction? I think it would be cool if we can. And just to kind of give you a little bit more ideas about this story. What is a simple models and versus complex models? Linear models are great. They are great, and here we always can get an explanation pretty much straight ahead. Uh, you can see here is an example of the temperature prediction. You can see, for instance, the weights in front of each feature, which contributes to the prediction value. Clearly, the larger the absolute value of the weight, the more impact this feature has actually. So the more with the contribution of this factor to the model prediction well, you would not disagree with that, because you say, okay, months of the year is really impactful, or okay, January is always much colder than June, whatever. Everything is nice with the linear models, but the problem that they cannot really perform well in case we need to explain complex and non-linear dependencies. So looking down, so you can see that the architecture of the deep neural networks can be pretty complex, and the face of your end user would pretty much resemble this yellow guy. Okay, just tell me how this magic thing works, and you will have really hard time to explain the all underlying mechanisms. Even the users are absolutely super happy with the performance they have. Few words to add here about the world of tools for getting you explanations. Just want to say it has a lot of dimensions, but I think there is a nice way to present it with the sort of two dimensions around. So I think that our colleagues, and namely Monsieur Elalami and Monsieur Noletto de Blackman AI, they have made a very good job. So here's a link to their presentation during the last Exhibicon. That was a really beautiful presentation, and they made a very good overview of the tools which you can place in each of these quadrants, or even in the middle of the quadrants. But the quote of Oprah Winfrey, it just here to tell you, yes, you can have it all. You could have something which can explain your model at the very local level. You can have something explaining at the very global level. Be it completely model agnostic, that means you can use the same tool for explaining pretty much any model you want, or it can be model specific, just to say very model specific, explaining one single type of the model. Yes, you can have it all. The problem, you just cannot have it all at once. And we need to do something about it. But for today's conversation and for today's examples, I picked Lime, which is based somewhere here at this quadrant. It gives you local explanations, and it stays reasonably model agnostic. Not 100%, but still very good. Okay, I'm sorry. Kind of have a hard time switching. So just to... something in jumping, I'm sorry. So just to, describe a little bit better why do we need to care about level of explanations in terms of the global versus local. So those of you who know the machine learning model based on the random forest, for instance, or some models based on the ensemble of the trees, they know there is a way to explain feature importances. So here is an example of the very well-known iris flowers classification dataset. Everybody who begins study data science probably use it for the educational purposes. But for our illustration, it works as well. It tells, like, if you take all your flowers in the train set and we try to understand what impacts the class to which the flower belongs, so we can observe that most impact in most cases, this is a petal width and the petal length, and then a little bit of the sepal width, and almost nothing to do with the sepal length. That's cool. That explains how the world goes for this particular subset of samples of the iris flowers. Why do we care our explanations to be local? So imagine we arrive to the future, we have a robot doctor, and you're as a patient, and it comes one day to you and says, okay, you need an urgent operation. And you just say, why? First, why me? And why do you think it's an operation in my case? And with metallic voice, he's gonna tell you, because my ML model predicted urgent operation for your case. Okay, makes you happy probably, but you still want to know why. And to give a local explanation for a single particular instance, like your particular instance, would be nice in this case. And that's why we really care to make our explanations local. Uh, moving to the other dimensions, moving to the other dimensions such as model specific versus model agnostic. Um, I want to illustrate here the thing with one example. Again, it's a tree-based algorithms which really have a cool thing called feature contribution. Since a recent version of sklearn library, there's a way to search through the whole tree, or each tree of the decision participated, a tree participated in the decision your model delivered. And there is a framework which is called tree interpreter. It makes this even more simple because it kind of goes through the each branch and each node of the tree, and it collects all the information related to a particular instance. And then we can imagine that our prediction can be represented by a sum of our contributions of each of the features which we took into account, plus certain amount of bias. And it let us say, okay, for this particular flower or for this particular patient, number 523, the model classified it as belonging to class 2. And it's absolutely great. It's absolutely great that now we know how to explain a single instance. But the decision of the model for this single instance. But this great tool is applicable only for the things like random forest or similar algos. So if it gets more complicated, if we're changing our model, if we are not satisfied with its performance, we want to do something, use something else, okay, we're losing this advantage of being able to explain model prediction for a single or particular instance. And that's why we want some tool which is gonna stay model agnostic. It will serve not only random forest, but everything which we want, which we can potentially use are to please our customers with the best possible performance ever. And here Lime comes. So just to repeat again that Lime is an open source Python framework. It stands for Local Interpretable Model Agnostic Explanations. And what it does, so for each individual instance, which means local, we pass the sentence to the model, we get a prediction, and the idea behind is very nice, very elegant. We sort of perform local sensitivity analysis and in order to understand how sensitive is the prediction around this particular tiny small region where our instance stays. You know, I added this 3D kind of chart, and I say, for example, we want to explain model prediction right here. And we literally can see that if we move along one dimension, the sensitivity would be lower. If we, for instance, go in the other direction and we try to understand if we change a little bit here and we change a little bit there, how it will impact the value the model predicts. And again, just to repeat that the beauty of the Lime that it stays model agnostic for most of the classical ML tasks such as classification and regression. I say for the most because you can imagine like there could be some tasks in the data science domain, such as, for example, a recommender system, which won't be so easy to analyze with a tool like Lime because the mechanisms of the evaluation of these models is kind of slightly different. To give you a better illustration, what I tried to explain with my hands movements and cursor movements around this 3D chart, I put a imaginary example here. So imagine we solve a classification task, and our function, which is separates class blue from class orange, is really very nonlinear, as you can see. So, and for instance, we want to get explanation for this big fat red instance we mark with X. So what do? We sort of create some surrogates. We perturb a little bit values of the features around X. And as you can see, our X's and our blue circles have different sizes. This just to say that, for instance, the closer the instance, the more impact it has on the prediction of the model at the point X. And you can find different functions for describing that, but normally it can be, in the most trivial case, it could be Euclidean distance, for instance. And you see, once we generated this sort of surrogates, this kind of perturbed instances, we get the original model's predictions for them because we know we have already learned values of the model for everything. And we kind of create a mini model here, right? So it's like a simple linear model because I think you got it. So the linear models are the most simple. They're not complex. They have a minimum possible complexity probably, which still makes sense, right? So it's like a single point probably has the least complexity, but you just cannot get anything out of that. And what we do, we just approximate the model well in the vicinity of our instance, and we get the explanation. So the generic formula for any explanation you can get with Lime is here under the chart. Just without going into much detail about mathematics, I'm gonna say that we need to minimize the error, which as a discrepancy between the original complex function f, our surrogate simplified function g, which has a lower complexity, which is not always possible to keep linear, but indeed we should try to do the best. And the p depending on the x, right? So this is something which we can use for describe the locality. That's what I talked about. So this is how many neighbors we take, how far we go, all that. And omega g here is the complexity. So the measure of the complexity can be rather different, and you can choose it depending on your specifics. But for example, it can be the degree of your polynomial, it can be the computational time for the original function f. So here there are a lot of variations, and in the conclusion I will mention this as one of the weaknesses of the Lime, because you see there are so many things which can impact actually the explanation you finally can get out of it. One more illustrative example to help you get the idea. In this case, it's a sort of a real thing, right? So imagine we're trying to predict the probability of cancer, and the only single predictor we use is the age of the person. And we imagine that the model learned very nonlinear dependency is our orange curve. It's complex, not so much, but still much more complex than the linear thing. And for instance, we try to look at the explanation for the patient who has 20 years and another one who is 60 years old. And you probably can guess here that based on this Lime approach explaining the value of the model, that around 20 years, the model coefficients are would be rather different, for the approximation model coefficients would be rather different than those of the local linear approximation which we build for one who is 60 years old, right? So meaning that when you are 20, the risk of a probability of getting cancer is pretty much stays flat, whether you are 15 or 25. When this dramatically changes when you reach your 60, and then plus or minus 5 years can mean something. So hopefully this example just kind of gives you the idea. Moving forward, with a simple example and one single dimension, I think it's fairly clear how the thing may work. And you tell me if it's not clear. You just show me something in the chart to say, we didn't get it. Can you repeat, please, from the beginning? Are you still with me? Can somebody me show something in the chart? Thumbs up. Say, we're unhappy. We left already. All. Okay. Good. Yes, I think this is a delay. I don't really get your answers are fast enough. Good. Yes, I remember about this latency. This is terrible. Sorry for this. Okay, and now we're gonna move towards a really practical application of Lime. So I took an example of text classification, and I used a 20 news groups dataset, and it's very well familiar to the people who study data science, because it can give you all the possible spectra of the emotions, from being super happy up to being absolutely confused when, for example, you try to practice do cluster analysis on this thing. For just to simplify my task here, and for the illustrative purposes, I left only 2 news groups. So we will not make a classification for 20 classes. It will be just 2 classes. For the pre-processing, I do only one simple thing. I vectorize the texts with using TF-IDF. And then I just take default simple SVM classifier, and hooray, as a beginner data scientist, you would be absolutely excited to observe, okay, your accuracy is 91%, super precision, recall 99%, F1 altogether 93%. Cool. And the question should have asked probably, really? Because if you've got already certainly some experience in your past, it can look pretty suspicious that you succeed so easily and so fast with getting pretty impressive performers for your classifier, especially before you do even any type of feature engineering or any type of let's say hyperparameter optimizations. So here what we can do, we can try to use the Lime text explainer, which lives inside Lime underscore text package. For this purpose, we packaged the steps of the pre-processing and classification into a single pipeline. And we take a particular instance of the text like I said, it's all local, and we take on a single instance, which is at the index 13. And we ask, okay, tell us what is the class, and we see true class, alt.atheism, predicted class, alt.atheism. The classifier is absolutely confident. Is there any reason to worry about it? Oh, I cannot succeed with switching. Okay. So, but indeed, there is a reason to worry a little bit about it. It's way too good, and this has made it suspicious. But in fact, it's really a handy tool to get the explanation of this type and kind, because with Lime, using one simple single line of the code, you can reach the representation of the explanation, which is gives you a text where the words contributing to each type of class are highlighted, and you also get the explanation which kind of supports the decision of your classifier. Only the problem which you can observe is that the classifier really picked a lot of garbage. Indeed, the content which it used it just happened. I think this is the way how the data set was prepared, that in this subset of alt.avis class, a lot of texts were selected from containing these technical headers of the emails, containing this different kind of parts of email addresses. And despite the classifier was right, it really didn't make a good, meaningful decision for the users. Because when we do the better pre-processing, we take away all this sort of garbage part, we can see that default performance really drops. Not absolutely dramatically, but substantially, significantly, because you can get quite a fight to increase performance of your classifier by 5%, and here we just immediately dropped by this no, I think more than 5%. We dropped down, and world doesn't look so much perfect anymore. And that raised the warning that made us think, okay, we probably need to preprocess most of the things before we feed into the classification model. And for better generalization in the future, if the texts arrive without these technical headers, probably the classifier will still perform, and it will not drop dramatically its performance only because of the reason and the way the data is supplied. And I think it's a good example to use. So the next one is the example of the Lime being applied for image classification with where we use DNN and Keras library, Keras framework. So I took two funny images. So there is like an internet, you can find this sort of confusion data sets where you can see dog faces and the muffins with raisins. And here we have the owl head and the custard apple. It's a kind of sort of exotic fruit too. It's not a real apple, but close. Same family. To solve classification task, I used pre-trained Inception v3 model, and here is the architecture. Now you can really appreciate an opportunity to get some explanations about this thing, because indeed the architecture is super performant, but it's also super complex. So we just will feed these two images and see what are the answers. And for the first case, we take the owl head. Hope you can see it already. We feed it in. We say, hey, who is this? And the model says, I'm not very confident, but it looks like a custard apple. Probably it is wrong. And at the second round, we try to do the same thing, because just we need to check if our model is absolutely silly. It just maybe don't know, never seen this. And we feed in the custard apple, and it says, we 99% per 99.99. So it's a custard apple. I am super cool. I solved your problem very well. What can help us in this case is just to look at the really and request explanation from using Lime. And for this purpose, we can use Lime image explainer from the lime .lime_image package. Again, pretty simple, few lines of code, and you get the beautiful explanation in two possible ways. Actually, it's more than that. But normally you can stop here, so you can make a mask where like the more deep color highlights or the parts of the image which mostly impacted the model decision, and the others which are kind of impacted it a little bit less, and the rest which just didn't impact at all. Or you can use a sort of mask. For me, it's a little bit strange that the mask doesn't contain all the parts highlighted here, but I think it's a way how it works. Maybe kind of bug in the tool, not sure. Sometimes it goes well, sometimes it does not. And we do the same thing for the apple and for the owl head, and we can see, wow, there are some similarities here which actually can prove that the model, despite it was wrong, it was not absolutely unreasonable. So yes, there is some rationale behind, like as a human being, like I think if I put these two images far enough from your eyes, you may also make a mistake. So why a model cannot? Hope I convinced you that the explainability and interpretability of the machine learning results is really important. It can add a lot of value to the daily work of data scientists. It can contribute toward building and creating trust at the user level. It can support decisions of the experts. So it can do a lot of good things. And just to conclude, Lime is great because it's easy, it's open source. It's let you explain single instance and tell why exactly in your case you need to be taken to the operation theater, even if you don't want. It still will help you to understand the rationale behind. And it lets you explain the model or predictions for pretty much any model. So it stays model agnostic, which is perfect. And it lets you represent explanations in the interpretable format, so you can easily take a look at the explanation you receive from the Lime and get, okay, I understand what this model is about. However, as I said, nothing comes for free. Lime has its limitations and drawbacks. So you think about choice of the hyperparameters, such as like description of the locality, measures of the complexity. That can make your explanations pretty volatile. So this means they will vary depending on what the hyperparameters you are choosing. So it's not stable, it's not always clear, but it's a lot of empirical knowledge. My expectation here, I think that people using it more and more for particular applications will come up with a sort of some rules of the thumb, some sort of best practices. And that will definitely make it more applicable. So Lime doesn't know how to deal well with the high dimensionality. So you need to do some homework before you really can feed in into the Lime. They think where you have a lot of dimensions. So because this is a well-known problem in the data science domain, right? You can, especially when you don't have too many objects and you have a lot of dimensions, so the distance is kind of shrinking, so you cannot really find. So the objects kind of in the multi-dimensional space, they kind of get all very close, and it's very hard to differentiate in between the objects which are far and the objects which are close. And indeed, Lime doesn't work anything for you here. So it just doesn't reduce dimensionality well, and it also does not really help you to do feature preselection. So you need to kind of prepare the thing for Lime. So this is not tool for this purpose, but once you arrive to get a nice model with a beautiful dimensionality, well preselected features, here you go. You have a chance to produce a nice, clear, interpretable explanations using this simple open source tool. And that's it. The time for your questions. Okay, for just, okay, I'm gonna try to check if I can see the questions in the chart. Okay, so I see one question which says you can come to a conclusion by using different paths. Likewise, different models can use different features, hierarchies to arrive to the prediction. Is it satisfactory for the end user? Uh, well, the perfect question, um, but it's not really a question to me. It's a question to your end user first to say, it depends. It really depends what your customer wants to know, what the user wants to know. Uh, Sometimes, yes, as I said, there are multiple dimensions of the space of explainability. So you can reach general explanations which explain how this world goes by, and your user can be satisfied with that. I don't have really kind of a single answer to that because I think it's necessary to study all the possible solutions to deliver explanations to your end users, depending what they're looking for, depending what their needs are. And there is a bunch of tools and techniques which exist there. So Lime is just one single tiny kind of uh, example. And I hope that that answers the question. Okay, so beside Lime, what methods would you try at first to explain a CNN? Um, okay, just I start to okay answering by this question. So I think, generally speaking, you can try to generalize this approach and try to explore the chain of the back propagation. This is for case of any DNN and particularly CNN. So I think it's a rather complex, and I really don't know if there is any kind of universal tool to do so. Um, but yeah, if you go back and at each stage of the back propagation, you try to apply kind of similar type of technique as a sensitivity analysis, it kind of more may work for CNN, but I'm really kind of don't have a good answer to that at the moment, because I never looked at anything specifically and precisely are aimed to explain our convolutional neural networks. Sorry for not kind of being helpful here. Uh, so for the, okay, this is a question which is for to be okay. That's precise. Question number one. So to be more precise, should we hide the complexity to the end user? Well, indeed, I think we should, but it's my personal opinion, and I need to say this may be caused also by the fact that in practice, our experts they use a different set of data. For example, uh, I had a project where data which typically used by the experts in the domain were not accessible, were not available. However, we succeed to solve the classification problem, but we had a super hard time to explain them why model came out with that decision unless we start to kind of using Lime for kind of illustrating what impacted the model decisions and time, because it's completely was different from the subset of the features the experts normally use for do this classification work inside their heads, uh, and trying to explain to doctors the way how the deep neural network works, I think it's also not super easy. So yes, we should hide the complexity. Mm, And do you think the ability of understanding the model can lead to a better adoption than other prediction? Okay, can lead to a better adoption than other prediction tools for a developer or a technical person that is not data scientist? Oh, indeed, I do. I do. I think it's kind of multi-purpose idea. So it can serve. Yeah. It can serve multiple purposes. It can help data scientists for not to make a really kind of silly mistakes. It can help users to develop a trust, or it can help users to kind of advocate for using more artificial intelligence and machine learning tools. So yes, the answer is yes. Um, okay, question. There are known pitfalls. What impact have this when overfitting? Okay. Uh, there are known pitfalls. What impact they have when overfitting? Poof. I never thought about that kind of connection which you can make in between the problem of overfitting and your and the opportunity to get the predictions. Um, Good question. I take it with me. I promise I'm going to think about it. Um, no, it's not like I can answer it straight ahead if I understand the question right. Anybody else? Oh, yes. Okay, that's a good point. Yeah. So it's if the generalization isn't good, the local explanation would be good. Uh, mm, Not sure. That still brilliant questions. Something to think about. Anybody else? Okay, for me, it looks like the questions flow is drained out and we can wrap up. So for the wrap up, I should say that we continue. Oops, I'm sorry. That we continue um, takeaways next week, and you are very welcome to join every day around the 1 right after your lunchtime to digest new dishes. Thank you for all who participated and enjoy the rest of your day. And good weekend. Ciao, ciao.